All right, on this section, we're going to go a little bit further into our chart that we made. And so I'd like to go ahead and review those things and see if you can do it without looking at your chart. So just thinking about what that chart says and just thinking about what functions do, this basically is saying when the derivative is positive, then f is doing what? And hopefully everyone can answer that quickly with increasing. So then when f prime is negative, f was decreasing. When f double prime is positive, it's concave up. And remember, that means it can hold water. And if f double prime is negative, that means that it's concave down. Okay, then we talked about what an inflection point is. And an inflection point is anywhere it changes from concave up to concave down or concave down to concave up. So it's just a change in concavity. All right, we're going to use that information now to go ahead and take a look at the first derivative test, and then we'll also use it for the second derivative test. Okay, we've also already talked about the first derivative test, but we haven't actually formalized it. So basically, the first derivative test, I just want you to think about if you would graph a function. So if you just graph a function that has some max and mins going on in it, okay, every time you hit a maximum point, so you hit that value here that's the maximum, what is going on to the left and to the right of it when you have those locals? So when it's a maximum, your graph was increasing and then it starts to decrease. So doesn't that mean that f prime is positive and then f prime is negative? So in other words, when I switch from positive to negative, I have a local maximum. And likewise, I'm now negative right here, and then I have my local minimum, and I switch from negative to positive, because I switch from a decreasing graph to an increasing graph. So when I switch from negative to positive, it has a local minimum. And now, even if I had, let's say that I had this graph continued, and let's say that I had a 0 tangent line. Let's say that I have a slope of 0. This one, I'm not changing from increasing to decreasing on the left or right side. Like there's nothing changing. It's the same the entire time. So therefore, there is no max or min. And we talked about that with Fermat's theorem. All right, so you can go ahead and read the second derivative test. Basically, it involves f prime and f double prime. So let's just think about this. If we refer kind of to a graph that just has lots of max and mins, let's talk about what's happening here. So when I have a maximum point, when I have a local max, so like say right there, then I have a slope of 0. So I know that I have a 0 tangent line here. I know that f of whatever the x value would be is 0 at that point. But then we also notice, is that graph concave up or concave down? And we notice that it's concave down. So that would mean that at that point where I have a maximum value, a local maximum, f prime is equal to 0, and f double prime would be concave down, so it must be negative. And that would be my local maximum. And now the same can be said when I have a local minimum. I know again that the f prime is 0. So f prime is 0. But if you notice, this is now concave up at that point. So f double prime must be greater than 0. So we don't actually have to graph this. We don't have to see this. There doesn't have to be a plug into the calculator or Desmos. You can use the first and second derivative tests to figure out if you have local max or local mins. And honestly, the second derivative test helps you more because it gives you more information. You don't have to test both sides. You know if it's concave up or concave down, that we don't just have a horizontal line. So the second derivative test comes in very handy. Now, how do we use the first and second derivative tests? Well, actually, your graphing calculator and Desmos, any device that has been programmed to graph these functions uses these tests in order to create the functions. So if you were going to be a computer programmer or you were going to be a programmer of some kind, these kinds of things will come in very handy, especially if you were writing a program that would graph functions. So let's just take a look at how this applies to graphing a function. So we have the graph of y equals 3x to the fourth minus 4x cubed minus 12x squared plus 5. you are asked to find the intervals of increase and decrease. So basically, we're going to go through this step by step and find all the crucial pieces of information, put them on the graph, and connect it all to make it look right. All right, so for A, intervals of increase and decrease we know come from the first derivative. So I'm going to find y prime. In this case, y prime would be 12x to the third minus 12x squared minus 24x, and the 5 would go to 0. And I'm going to find my zeros, because remember, to find our intervals, since this is a continuous function, we find those zeros, and then we test each interval to see whether it's positive or negative, and then we can conclude whether it's increasing or decreasing. So off to the side here, I'm going to go ahead and set this equal to 0, and I'm going to factor out a 12x while I'm at it. So just from being able to factor out a 12x, I know one of my zeros is x. Or sorry, one of my zeros is 0, because I have 12x for my first factor. And then I have an x squared minus an x, and then minus 2. And now I notice right away that that's factorable fairly easily anyway. So I have x minus 2 and x plus 1. So it looks like my three zeros are 0, 2, and negative 1. So therefore, my intervals that I need to test are going to be from negative infinity up to negative 1, from negative 1 to 0, from 0 to 2, and from 2 to infinity. And however many critical numbers you have, you will always have one more interval to test than that number. So we had 3 critical numbers. Here we're going to have 4 intervals. Okay, so now you can just plug in a value. So pick a value within the first interval here. So pick some value in there, maybe negative 10. And if I plug negative 10 over here into this factored function, I would get a negative. So I'd have a negative for the first term, I'd have a negative for the second term, and I'd have a negative for the third term. So that would be negative. And now you can repeat that process and plug in numbers, like you could plug in a half, negative a half for the next one. And when you do that, you end up getting a positive answer. You can plug in 1, and when you do that, you end up getting a negative answer. You can plug in 10, and when you do that, you get a positive answer. Now, a lot of times it does just alternate between like this, but not always. So that can be deceiving, so don't assume that it automatically does. Okay, so looking at this, we have our intervals then. So here we have an interval of decrease, increase, decrease, increase. We have our intervals of those. And then we learn from the first derivative test that if we switch from a negative to a positive, we have a local min. So we have a min here in between those. And then from a positive to a negative, we have a max. From a negative to a positive, we have a min. So in other words, if we were going to actually answer then letter B, it says, what are those? Well, we'd have mins for f of negative 1 and f of, looks like 2. And we'd have a max for f of 0. Now, you can go ahead and grab your calculator if you want and pause the video and plug those into the original function, and you'll get your y values, or you can take my word on it. In this one I got 0, this one I got 5, and this one I got negative 27. All right, so we have A and B done, and now we need to look at our intervals of concavity here. So we know that if we want to know whether the graph is concave up, concave down, we know that we need to do the second derivative. So I'm going to go ahead and do the second derivative here. We're going to have 36x squared minus 24x minus 24. And I notice that I can factor a 12 out of that. So I'm going to do that. I'm going to take a 12 out, but at the same time I'm going to set that equal to 0, because just like in A, we need to figure out what our zeros are so we can find the intervals to test. So at 0 equals, if I factor out that 12, I end up with 3x squared minus 2x minus 2. And then that one, you can go ahead and either polysimult on your calculator, or you can use the quadratic formula. I just polysimult it, and I got that if I have x equal to, looks like 1.2153 and x equal to negative 0.5486. Those are good decimal approximations for those. So those are going to be my zeros, or close approximations for those. So that means that the intervals that I need to test are negative infinity up to negative 0.5486. And then we will have the negative 0.5486 up to 1.2153. And then we'll go from 1.2153, to infinity. And so we're going to test those. And again, I just simply want to know, is y double prime negative or positive on each of these intervals? So I pick a value. I picked -1 for the first one. So I picked -1 for the first one, and in doing so, I got a positive value. And then I picked 0 for the next one, and I got a negative value. And I picked, I think I picked 2 for the next one, and I got a positive value. So I am concave up here, and concave down here. And so now if I need to find the inflection points, well, the inflection points are obvious from this because it's where I changed from one to the other. So I would have, see, inflection points are going to be f of, looks like 1.2153, and that's about negative 13.4, and f of negative 0.5486, and that's about 2.3. All right, and now our last task is to go ahead and graph all of this. For that, I'm going to go ahead and go to another slide, and we'll put all this critical information down on it, and we'll connect that graph. All right, so we are ready to graph this. If you look at this graph, I put the y's, they're going by 5s. I wrote that off to the side here, and the x's are going by 1s. So we're going to put all of our crucial information on here and then just connect it all. So I'm going to first start with our maxes and our mins. So we have a maximum value at f of 0, 5. So since these are going by 5s, I know that's right there. And then we also have minimum values at -1, 0, and at 2, -27. So that would be about right there. All right, and now we are going to put on the inflection points. The inflection points are about 1.2, -13. Let's see, it'd be right about in here. And at -0.54, 2.3. So somewhere right in there. All right, so we have our inflection points, we have our local max and mins. All right, and now we know that this function starts off decreasing, and it decreases till it hits our minimum, and then it starts to increase. And we also know that it starts out concave up. So it's going to start out concave up, hit our minimum, switch to concave down, hit our maximum, switch to concave up, hit our minimum, and then come back up. And that's just kind of the basic flow of the graph. So hopefully you can see all those crucial pieces of information there in the graph, and that these two tests make sense to you. Come in and get some help if you need a little more assistance on it.